Speaker is Rory O'Sullivan. Rory obtained a first-class honors in mechanics and manufacturing engineering. Dismayed by the stagnant nuclear industry, he started his career with the Bouygues Group, an international construction company working in several sectors. His interest in the innovative nuclear sector has kept him up to speed with new technologies since 2008. The discovery of MSRs led him to be a co-founder of EPD in 2013, where he was a project manager for this feasibility study. Today, he will talk about feasibility study of a pilot-scale molten salt reactor demonstration. Please, you have the floor.
Thank you very much, Dr. Rivel. So, we've heard numerous times over today and yesterday that molten salt reactors really are the best technology for harnessing the power of thorium as a fuel. So taking this on board about 2.5 years ago, we saw the need for this project. And the project, to say, is looking at, is a molten salt reactor prototype really feasible? In particular in the UK, because we have UK funding, UK government funding. In addition, we looked at the MSR status of activity internationally, and we did an evaluation of the various commercial designs that exist. So to do that, we set up this company, Energy Process Developments, myself and 2 others, one of whom is Trevor Griffiths, who actually worked on the experimental reactor in the 60s. But before I go into that any further, I just want to make clear the report of our study is actually available to download for free online. You can see the website at the bottom there, energyprocessdevelopments.com. Or if you want a hard copy, you can go to Amazon. If you search for MSR Review, you can buy it for a few quid there. So, once we set up the company, we had a few aims, one of which was to make people aware of the characteristics of molten salt reactor technology. It was also to make sure that it can be a step towards resolving the global energy poverty, and to make sure a pilot scale plant happens somewhere, either by us, by someone else, by a nation. Doesn't really matter as long as someone does it. This all started because 2.5 years ago, nobody else was doing it. First step towards this was to carry out a feasibility study. But before I go any further, most of you should know what a molten salt reactor is. Just briefly, for any of those of you who don't, this is a very generic molten salt reactor here, actually from the Generation 4 forum website. The fuel salt is a liquid and circulates through the core, typically in a graphite moderated core, but that changes. As the fuel is liquid, you don't have a meltdown. That accident scenario just doesn't exist. It operates at higher temperatures, so you have higher efficiencies. Most of the fission products, the troublesome ones, the gases, bubble out naturally. You can assist that with the various reprocessing techniques. And you can use various fuels, plutonium, thorium, uranium. It's quite flexible and diverse. All of these benefits bring one main thing, and that's it can be a cheap technology. It can be, the cost estimates at the moment come out on par with coal, and that's what's really revolutionary here about this. If it's so good, why isn't there one? It's the question most people ask when they hear about it. Well, there has been. The very first one was a molten salt reactor built by the US Air Force. It was built for an aircraft, ran for 100 hours successfully on the ground, and they built it cold up in the air. It was a ludicrous idea, so thankfully it didn't actually take off. Flying radioactive liquid above your heads, not great. Thankfully, not thankfully, but the intercontinental ballistic missiles were invented that stopped that. But it did lead on to the successful MSR experiment, which ran for 4 years at 8 megawatts. Most of the designs we see today actually originated from that concept, along with the 2.5 gigawatt breeder version, which is a design done on Outgrid also. That's well known. What isn't so well known is the other MSR activity that went on internationally around the same time. In particular, this is a design from the UK. It was built to be 6 gigawatt on a factory line. It was a molten salt in a chloride solution. Unfortunately, this stopped around the same time as the American project stopped, and effectively nothing happened until really 2002. In the Generation 4 forum, molten salt reactors was chosen as one of the 6 configurations for future development. So the first step, our feasibility study, it was a year-long study funded by a UK government grant. We'd look at various MSR configurations, so it's not research and development specifically. We'd look at the licensing regime, look at various sites in the UK, and carry out a public opinion poll on advanced nuclear. We also wanted to have a look at the role of a prototype in the UK. First step to do all this was to gather a team, so we had quite a strong supervisory panel. Professor Derek Frey, Director of Research at University of Cambridge, Professor Paul Madden is Chemist and Provost of Queen's College, Oxford, and Dr. Jeff Parks is Senior Lecturer in Nuclear Engineering in University of Cambridge. In the middle are the 3 project directors, and then we had a large team. The bulk of the work was done by Fraser Nash Consultancy, one of the leading nuclear engineering firms in the UK. We had a recently retired regulator, David Glasbrook, on our team, nuclear engineers and various others. So the first step after that then was to actually look at the MSR scene internationally, and obviously this is led by the Chinese. They have a program going on, about $500 million with 600 staff. As part of this study, I went over to visit the researchers there in March, and you can really see in Shanghai the pollution affects life. If you look in the bottom left here, you can see the blue photo, very nice. It was taken when they shut down all of the factories and, well, dirty factories, let's say, around Beijing for APEC conference. On the right is a photo of a normal week. The Chinese need thorium molten salt reactors. They need clean fuel. They have to do something about it, and that's why they have this large program. It's not going as quickly as they planned. Their staff are very young. Out of the 600 people, the average age is 31. But they're really trying to get the basics and then move on forward. There's a lot of collaboration going on with the United States at the moment. The Chinese are looking for a 2 megawatt liquid prototype first, along with a 10 megawatt solid version, which is in development now. And the collaboration with the States is on their solid fueled FHR. So we also visited Oak Ridge, where the core of the solid fuel molten salt work is. You can see a photo here, myself and another team member, Jasper, standing in front of the MSR experiment building as it stands today. Basically a big shed. That's how simple these things can be. We were quite lucky that we managed to park across a no parking sign in front of this building when we got there. And the friendly Americans, instead of saying, get lost, they said, can I help you? So we explained what we're doing and the project, and then a couple of minutes later, we had the person responsible for the building take us inside and show us nearly everything except the reactor core. So it hasn't really changed at all. It's left as it was, but we saw how simple it was. Some of the other activity internationally, we heard a bit about the SAMAFAR program and the molten salt fast reactor. I won't go into that any further. But then we shortlisted 6 designs. These are really the commercial designs. So we'll have a look at a couple of them. Many of these guys are here, speaking today and tomorrow. Transatomic Power. Thorium reactor is really based on the MSR experiment, based in Florida and the States. They'll be presenting tomorrow morning. They're thorium uranium fueled. Moltex Energy has a stable salt reactor, again presenting this afternoon. Terrestrial Energy have the integral molten salt reactor, and Seaborg Technologies with the Seaborg waste burner, and Flybe Energy presenting later on today with the liquid fluoride thorium reactor, the lifter, and that's a 2-fluid breeder based on thorium. So if I just take an example, the integrated MSR with terrestrial energy, you can see the main difference here with this design. Everything's integrated in one replaceable unit in the core. Oops, hold on. This here has a lifespan of 7 years, so they don't have to worry about lifespan of the moderator and some of the key components. They can just replace that. It's low enriched uranium and with a graphite core, and they're based out of Canada, looking to get a inactive prototype up and running pretty soon. Next is Transatomic Power. These guys are based out of MIT in Boston. They are really sort of a .com model. Their reactor works in the thermal epithermal region, and The big difference with this is their moderator is zirconium hydride. They see a lot of benefits with that, particularly when you mix uranium and spent nuclear fuel with the plutonium, as we heard, I think, yesterday, the benefits of that. Another example is the stable salt reactor from Molten Energy. That's a pool-type reactor that operates in the fast spectrum. And the big difference here is the fuel is a chloride salt which is static. So it's not pumped, it's in fuel tubes. You can see a blown-up version over there. Again, there'll be a presentation later on about that specifically. So the process to look at these, to make a short list of all the activity and the designs that exist, because there's a lot of them around the world, we needed to have a molten salt as fuel and coolant. Some configurations just have a molten salt as coolant. They needed to have a commercially active team to actually do something and get a pilot scale plant built, and particularly in less than 10 years is the restriction. The technical review most of it was done by Fraser-Nash Consultancy. They looked at material selection and handling, safety analysis, operability, and the big one is licensability. Most of the interesting review came from that section. Some of our team looked at the fuel cycle. There was our nuclear engineer, Andre Hervet. From a regulator's perspective, there was David Glasbrook. The molten salt chemistry was done by Trevor Griffiths. He's the one who worked on the experimental reactor. And then there was an economist's analysis of the situation done by Atkins, another leading engineering firm in the UK specializing in nuclear. So taking all this information together, we were able to class the different reactors and give them scoring on various headings. You can't see very clearly here, but effectively you have some main headings: the technology, safety in the environment, security, the simplicity, licensability, and then general characteristics. So several people from the team gave input, and we had international input from the International Thorium Organization in Japan, and Thorium Molten Salt Organization in Japan, and from Oak Ridge. What emerged out of this was the Molten stable salt reactor came out as most suitable for UK implementation based on a few reasons. There's no pumps, so for engineering design it really is a lot simpler. It uses existing technology because they're fuel tubes. It's got a lot of similarities with today's reactors. It doesn't use new materials, so it can use existing steels from the nuclear industry. And what's relevant to us is it's UK design, so it's UK intellectual property. And then again, relevant to the UK is it can burn spent nuclear fuel very efficiently. Other things that are relevant from our study that we picked up at our regulatory review, the UK actually is quite good for looking at for looking at a new innovative reactor design. It can happen there as opposed to other countries it can't. But obtaining a new site license is a lengthy procedure which you really want to avoid. So we've specifically looked at existing sites. A process does exist for experiments in the UK, but there hasn't been any experimental reactors since the 70s, so that experience just isn't there. The last reactor that was built was in the early 90s, the pressurized water reactor. And then the ONR, there are new PWRs, LWRs being built in the UK, so ONR are busy, basically. They don't have the capacity to deal with these new challenges. The main reason why an innovative reactor would nearly be unfeasible in the UK, but the final conclusion that it was, and it should be done as fast as possible. Some other, let's say, obstacles, mostly relevant to the UK. The Environment Agency, it's a lengthy procedure, but relevant. They work hand in hand with ONR. If for under 50 megawatts, it's a local planning process which would simplify things. The Department of Energy is ThEC, need a justification for any new radioactive substance. You need a decommissioning funding plan. Particularly relevant for liquid fuels, you need IEA, agreement for how to monitor the fissile movement, and then you'd need cooperation from WANO and the operators generally. Looking at economics, the National Nuclear Laboratory looked at small modular reactors being comparable with the new PWRs, Hinkley. The costs are £84 per megawatt hour, which is close to the strike price at Hinkley, $92.50. MSR vendor capital costs are really coming out quite affordable. They're coming out comparable with coal from several of them, depending on the design. at £2 a watt. That's what's really going to change the scenario here. This is affordable, and the technology is ready basically now without further science. Also, MSR fuel costs are slightly lower due to the higher burn-up. Not that relevant because nuclear is cheaper. And then operational costs are pretty similar. Just briefly looking at the public opinion in the UK. So we did a survey of over 1,000 people across the country, and there was some interesting new conclusions. 21% prefer new nuclear of a known technology, as existing technology, and 36% prefer technology that challenges the old. So effectively, you could say that's the Gen 4 sector. You couldn't see that as 57% in favor of new nuclear. Another interesting one is 23% have actually heard of Generation 4 technology, which we were quite surprised about. But 73% believe they need more information. That really enhances the point of a need for a prototype. People need to learn about the technology, the molten salt characteristics, and we believe the first way to do that is get one built somewhere. So just to reiterate, our report's available online there, energyprocessdevelopments.com. Please have a read, and thank you very much.
Thank you. So the floor is open for questions. Please raise your hand. There is one right there.
One major bottleneck problem in the MSR is a material, construction material. So what is solution for this?
A problem for the material of molten salt reactors, is that right?
Since it is aggressive, if you are going for fluoride material, any material cannot be lasting long due to corrosion. So any development to this is going on.
So the material is probably the first thing that people say that holds back the development of molten salt reactors. Actually, the material problem was really resolved in the 70s, shortly after the MSRE. They continued working on nickel-based alloys, in particular Hastelloy N. It's very resistant to corrosion in these environments. It's not a certified nuclear material, which is why a lot of the designs today have gone for stainless steels, very standard stainless steels. And the reason they can do that is today we know how to monitor the corrosion, that we can make sure the chemical balance is correct, that we don't have corrosion at all. So it hasn't been done yet, but all the simulations look like stainless steel 316 is absolutely fine, and that's the way everybody's going.
Even Hastelloy N itself is going after certain time of use, embrittlement cracking. So how monol 316 material can withstand?
I'm sorry, could you repeat that, please?
Hastelloy N, you told, no, that was a earlier thought material for the construction. So any alternate for this?
So nickel-based alloys are very resistant to corrosion.
But they are prone to dissolution corrosion in the molten salt, fluorides. Nickel gets easily dissolved, forming nickel fluoride. So it is not best for the fluoride-based molten salt reactors.
It's not very relevant for chloride-based reactors. I think I caught that. That's true. However, for the fluoride ones, the Hastelloy N, there has been reasonable amount of experimental data. There still does need to be more, but any more than that, I think possibly the speakers later on, some of the vendors might be able to answer that a bit better. I couldn't quite catch the full details of the question there.
Behind you there, near the camera.
Thank you very much for your presentation. My name is Carlo Vitanza from Norway. When we test, when we introduce new cladding material for light water reactor fuel, even if we have experience of decades in many countries, it takes normally quite a process before a new material is introduced. And so you have to go through testing a test reactor and then a lead test assembly and so on and so forth. I'm a little bit surprised that we moved to building a reactor without having an experimental basis for having chosen the material that is most appropriate, or at least assessed what the risks are, I think it would pay off if we do some autopilot testing, or maybe testing a test reactor to make an assessment of the material that you would like to use. Do you have plans to do that?
So I mentioned briefly there, Hastelloy-N is the most commonly employed material in molten salt reactors. You're very correct that that does need further experimental data, and you could probably add 4 years to the program of getting a prototype up and running if you use Hastelloy-N, because it needs a long time in a reactive environment to get the right data. However, one of the reasons we took the Molten stable salt reactor, it uses today's materials, it uses standard stainless steels, ThEC15 as one example, and there's a lot of data on those materials. So we don't need new data on that. We do need corrosive data, so we need to get experiments looking at molten salts in a corrosive environment in these steels. However, that does not take years. That's a much simpler process. The real radioactive data, the radiation analysis has been done for these materials.
Any other question from the floor? Yes, one right there. Bill?
Thanks for the exposition. I really appreciated it. My question is around this first-of-a-kind prototype, and I appreciate it is first-of-a-kind prototype. With that particular machine, what's the plan for the spent fuel and the back end? Is it going to go straight to waste in the prototype?
The various vendors have different strategies, and some do have the strategy, basically leave it there and you can nearly vitrify it directly. It's the biggest sector for molten salt reactor design generally that needs to be addressed. It's all being done at lab scale. It needs to be built up. For that design, effectively it's very similar to reactors today in that you can take a fuel array, you leave it to cool for a number of years, and then you can treat it by pyroprocessing various methods. The bismuth separation is usually the most common, but the various vendors have different solutions. I expect they'll have discussed their solutions later on as well.
All right. If there is no more question from the floor, then I'd like to ask one question myself, or rather a comment. I see that you quote the cost of electricity up to 3 figures. I hope you don't believe those numbers too much, because as I mentioned at the end of my talk, until a system is built, you cannot really know precisely the cost. I mean, maybe you get an idea, but I remind you that in the US, the cost of nuclear electricity changed a lot, because you have regulatory commissions that come and ask you to add all kind of things in addition that were not foreseen from the beginning, and in the end things cost a lot more than you think. I don't know if in your cost estimate you include what to do with the waste, with all kind of other aspects, and so my advice to you, don't believe too much the numbers you quote.
Well, I'll just add, yes, we're taking these, Energy Process Developments are taking these as vague figures because we've looked at the costings from the various vendors, and there's a lot of similarities. Some of them have not done them very well. They haven't taken the real nuclear factor into consideration. But some of them have been done by independent costers in the nuclear sector, so they know how the costs have gone up. And some of the unknowns, they've taken very conservative estimates. They know what needs to happen from an engineering point of view, and there's the amount of unknowns when they've taken such conservative estimates, really quite small. The actual cost of the regulatory burden as a percentage is quite small. There's only so many extra features you can add on to a molten salt reactor when it's got that intrinsic safety.
Okay, thank you. So if there is no more questions, I would like, on behalf of the organizing committee, give you a little gift in appreciation of your hard work. Thank you very much, Rory.